So in section 11.1, 11.2, we're going to talk about solving systems of linear equations using matrices. And this hits our SL number 5. And we'll be able to find the dimensions of a matrix, convert between a system and an automatic matrix, apply elementary operations of matrices, solve a matrix using Gaussian elimination and Gauss-Jordan elimination, identify inconsistent systems, solve systems with dependent equations, and solve applications using matrices. So a system of equations consists of two or more equations. A solution to a system of equations is a point that satisfies all the equations of the system. In this section, our focus will be solving systems of linear equations. If we're solving a system of two linear equations, two variables, there are three possible types of systems we could have. The first type is when we have a consistent system. The equations are independent. You get two non-parallel lines intersecting at a point. So our solution be where they both overlap. In this case, it would be the point 2, 1. And the way you can tell if you have a system of linear equations that is consistent is the slopes of the lines are different. The second one is an inconsistent system. The equations are still independent, but this time the lines are parallel. They never intersect. They both have the same slope but not the same line. So this system would have no solution. The third type is a consistent system where the equations are dependent. That means they're actually the same equation. Every point is a solution on the line. We write the solution as a set of all c minus by over a comma y, and the lines are exactly the same line. We will use matrices to represent a system of equations. So if I have a set of equations of 5x minus 3y equals 13 and 4x plus y equals 7, I'm just going to write down the coefficients, drawing a line where the equals would be, and then, so I'm not writing the variables, I'm just writing down the numbers I see. And say if I have a 3 by 3, I want to do the same thing. Now, it's important that your equations are in standard form. So I have to have these in order. I have to have these in alphabetical order and constants on the other side. If that's not the case, I need to do some rearranging first. Now, this first matrix here has 2 rows and 3 columns, so we say its dimension is 2 by 3. And this matrix has 3 rows and 4 columns, so its dimension is 3 by 4. We say it's a 3 by 4 matrix. We always classify the matrices by the number of rows and then by the number of columns. Think of RC Cola, rows first and then columns. So here's a formal definition. An m by n matrix is an array of rectangular numbers with m rows and n columns. So row 1, row 2, all the way through row number n. Column 1, column 2, all the way through column some n. Each entry, a sub ij, is in the matrix has two indices indicating the row I, the first number, and the column j, the second number of where the entry is located. Hence, a sub 43 does not mean 43, it means the number that's in the fourth row, third column. In writing an all-metric mix to represent a system of linear equations, we need to have the variables in order on the left side of the equation and constants on the right side. Also, if there are any variables if a variable is missing, we will need to use a 0 as the coefficient. So let's take a look at the workbook exercises 1 through 7. So we'll turn a few pages here. And so we want to write an augmented matrix for each system. So the first thing I want to notice here is that I am missing my x term in the second equation. So I'm going to put 0 as a placeholder there. Again, I just write down the numbers, 3, negative 1. I'm going to draw a line. That's where my equal sign is. And this should be an equals. So let's correct that. And I'm going to put my 10 in square bracket. This would be 0, 5, and 12. We'll do the same thing for the second one. 2, 3, going to draw my line, 1, 6, negative 4, negative 14. Now this one is missing some variables. So the first equation is missing a y. So when I do my matrix, I'm going to put 1 for the coefficient of x, 0 for the coefficient of y, 1 for the coefficient of z, and my answer negative 1. There's no coefficient of x, there's no x, so I'm going to put 0 for the coefficient of x, 1 for the y, 2 for the z, and then my 5. And then this one's kind of messed up here. No coefficient, so there's no x, so the coefficient of x will put 0. My y, this thing's out of order, so I'm going to put the negative 1 here, and then my z. So I want to think of this as being a negative y plus z for that equation, and then my 3. Number 4 and 5, we're going to go backwards. So this would translate into x equals negative 3, y equals 0.05, and z equals 12. This would translate into negative 8x plus 7y equals 113, and 2x, no y, equals 1/3. Now something to notice that what you want to do is you want to be able to eventually get your matrix in this form, because then you can just read off the answers. So we want to be able to take matrices that look like this or look like this, transform into something that look like this. For us to be able to do that, we need to look at what row operations we're allowed to do. So these are our elementary row operations. So we can do these operations without affecting the solution. We can interchange two rows. Row sub 1, double arrow, row sub 2 means interchange row 1 and row 2. So I can swap rows. I can multiply a row by a non-zero constant. So here we want to multiply row number 1 by 3 and made that our new row number 1. So notice I just take 3 times 3 is 9, 3 times 2 is 6, 3 times negative 5 is negative 15. And then we can add a multiple of a row to another row. So we take 2 times row 1 plus row 2, and that becomes our new row 2. So when we do that, and let's just kind of do the math on that. If I take 2 times row 1, that would be 6, 4, negative 10. And then I put my row number 2 underneath it. 1, negative 2, 10. When I add these up, 6 plus 1 gives me the 7. 4 minus 2 is 2. Negative 10 plus 10 gives me 0. So let's go ahead and do some problems here. And so they're telling us what operations we need to do. So I want to take 1/2 of row 1 and make that answer my new row number 1. So basically, I'm going to take each element in row number 1 and divide it by 2. And then that answer is going to become my new row number 1. So that will give us -1, 2, and 5. Going to copy down row number 2. Next, I'm going to go ahead and add row 1 and row number 2 together. So I'll just do it down here real quick. So that will give me my new row number 2, because that's where we're putting it. Oops. I think it's a 0, 7, 8. So my row 1 stays -1, 2, and 5. But now my row 2 is 0, 7, and 8. Let's try this next one. And looks like we're taking the opposite of row number 3. And we're going to add to row number 2, and that's going to become our new row number 2. All right, so the opposite of row number 3, so that'd be -2, -1, -7, 0. We're going to add to row number 2. And when we do that, that will give us our new row number 2. That'd be 0, -9, -3, -18. And so now our matrix now we didn't touch row number 1. Row number 1 is still 12, 0, -6, and 3, and we still keep row number 3. 2, 1, oh, there's something wrong there. Let me get that 2 a little bit closer. There, that looks better. So I didn't touch row number 3. It's the only thing that changed here is row number 2. So now I want to take each number in row number 2 and multiply by -1/9. So I'm just going to be dividing it by -9. And that's going to give us 0, 1, that reduces to 1/3, 2. And then that's going to become my new row number 2. So row number 1 is still the same. Row number 3 is still the same. The only thing I've changed is row number 2.